Started now.
Okay, here's a candy. And are you hungry, Sam?
I'll take candy.
Oops, sorry. All right, so let's see. We were, I was at the point of starting to talk about fermionic path integrals. And that's something that's, I think, worth doing just because it's interesting and amusing. In fact, something like more than 20 years ago, Roy Glauber and I wrote a paper on fermionic coherent states and path integrals. Anyway, let me go to the right section here and start the fermionic stuff. It's the way to think about this is the way one thinks about abstract mathematics, namely you're setting up a consistent system of some definitions and as a consequence of those definitions, certain things follow. And these certain things that follow, physicists write these things in the same form as ordinary integrals and derivatives. But you can't look at these expressions and say that they have to be the way they are because that's the way ordinary derivatives and integrals are. So it's all a matter of definition. So the first thing is, let's start with a single Grassmann variable. And the essential feature of a single Grassmann variable is that its square is 0. And that means that if you have a function of a Grassmann variable, it can be, I might as well follow the notes, it can be a constant plus another constant times the Grassmann variable, but you can't have if you have c theta squared, well, this thing is equal to 0. And so the largest, the most complicated function of a single fermionic variable is simply a linear function with 2 coefficients. And that means that one can construct a table of integrals very simply. Namely, the integral of f of theta d theta is going to be the integral of a d theta plus the integral of b theta d theta. And so what we really have to figure out is what's the integral of d theta and what's the integral of theta d theta, and then we're essentially done. So this means that for Grassmann variables, the table of integral is even simpler than the one that that graduate student at MIT used in his artificial intelligence program, where he had only 26 integrals in his table, and the program was actually able to integrate essentially the integrals on the final exam, the second semester calculus at MIT. So what do we want this to be? Well, what we want is we want the integral of f of theta plus zeta d theta, which of course would be an integral of, let us say, a plus b theta plus zeta d theta. We want this to be a plus b zeta times the integral of d theta plus b the integral of theta d theta. Because we want, so that's what we want, and in order for this to be true, then what we need is that you see this term here. We want this, sorry, I forgot to write the rest of it. We want this to be the same as the integral of f of theta d theta, which of course is simply a, the integral of d theta, plus b, the integral of theta d theta. So now we want to compare this with that. And what we see is that we've got a problem with integral of d theta, because here it's multiplied by a, here it's multiplied by a plus b zeta. So that means that the first rule is integral d theta is equal to 0. The second one works though, because the rest of it is b integral theta d theta should equal b integral theta d theta. So the integral of theta d theta is arbitrary. And so what we do is we just set it equal to 1. So that's Grassmann integration.
So I have a question.
Yeah.
Really quick. Why is f of theta, why are the two integrals equal to each other? F of theta plus...
Oh, you want it? Well, because what you want, of course, is you want to say in general, if you have f of x plus c dx, you want this to be the integral of f of x dx. The idea is you're integrating over all x. Here you're integrating over all theta.
So zeta is just a constant.
Zeta is a constant, a Grassmann constant.
Got it.
Or for that matter, yeah, a Grassmann constant. Okay, now, so these are the two rules. Now, because of, I guess because of antiparticles, or equivalently because we want to have creation as well as annihilation operators, we want also to have, for every theta, we want to have a theta star. And in particular, we want theta star to be Grassmann, so theta star squared should be 0. And we also want theta and theta star to anti-commute.
Wait, sorry, what about the second condition? I don't see why it should necessarily be 1.
Oh, that's arbitrary. No, it is arbitrary. We just set it equal to 1. Since it is arbitrary, we want to make life simple. You know, we could set it to some irrational number that is not even well known. but that would just make life difficult.
Yeah.
Okay, so now we have an integral table for theta star, and just to save chalk, I'll say what it is. It's that those integrals also are either 0 or 1. And let us say that psi is an actual fermionic variable. So we have psi squared is 0, psi dagger squared is 0, and psi and psi dagger anti-commute with each other. And then, just to make the bookkeeping simple, I suppose we could have psi's commute with Grassmann variables, but we don't do that. We say that the Grassmann variables commute with the fermionic operators. All the Grassmann variables commute with all the fermionic operators. And we're going to have, oh, did I have 0? No, that's not 0. That one is 1. It's rather that psi with psi, well, psi squared is automatically 0. Okay, so that was a mistake. So if we have one fermionic operator, we're going to say that psi and anti-commutes with psi dagger and gives us a 1. Sort of an analog of the delta function. Okay, the next, so these ideas are sort of all of one piece. The next idea that's new is kind of interesting, as is much of this stuff. First of all, we pick a state, S, such that psi S is not 0. So psi is the annihilation operator, and we pick some state such that some state that psi does not annihilate, and it doesn't matter which state we pick. We just pick a reference state, some fiducial state, and that's the one that we use. On the other hand, what we do next is we define for this system with just psi and psi dagger and theta star, we define the vacuum state or the ground state as psi on the reference state. And you notice that this is a sort of clever definition, in fact almost a comically clever definition, because this means that psi annihilates the vacuum, and it does so because it's psi squared on S, which is then 0. This is all in the online class notes. Okay. Next, we're going to define a coherent state, fermionic coherent state. And, or equivalently, since we're in this fermionic world, it's just an eigenstate of the operator psi. And the one that works is this. Suppose theta is the Grassmann variable, then this is going to be e to the psi dagger theta minus a half theta star theta on the vacuum. And so it kind of looks like a bosonic coherent state. It has something in common with it. And of course we can expand this exponential very easily. The first term, of course, is 1. The next term is theta dagger, psi dagger theta minus a half theta star theta. But any higher term vanishes because it would have 2 thetas. And so this multiplies our vacuum state. Now the next business is kind of funny. Psi on theta is, of course, psi on this structure here, 1 plus psi dagger theta minus a half theta star theta vacuum state. And what happens here is that psi on 1 annihilates the vacuum, so that's 0. Psi times 1 times 0 is just 0. This one gives us psi dagger theta 0. And then psi on the third state, well, psi anti-commutes with the 2 thetas, but then it hits the vacuum and annihilates it. So that one's 0. So this is the whole story. On the other hand, this rule here says that psi dagger is equal to 1 minus psi dagger psi. And so we can rewrite this as 1 minus psi dagger psi theta 0. On the other hand, psi anti-commutes with theta and annihilates vacuum, and so this is actually just theta vacuum. And so at first you'd say, well, this is no good as a coherent state because we want psi theta to be theta theta, but notice what theta theta is. Theta theta is theta times this, So it's theta times 1 plus psi dagger theta minus a half theta star theta vacuum. And now, what do we get? Well, the theta gives 0 on the second and third terms because theta squared is 0. So this is just theta 0. So this second equation, which is psi theta is equal to, let me, where is the eraser? Theta 0, but theta 0 is theta theta. So we have this theta that we've defined really is effectively a fermionic coherent state. We can define this is the corresponding bra, but for a different fermionic variable, say zeta. Zeta would be 0, 1 plus zeta star psi minus a half zeta star zeta. You might wonder why I'm using Greek letters. It's because I think of Grassmann variables as really weird, and so they deserve Greek letters. Yeah.
I was going to ask, did we have a rule for when theta hits psi dagger? Like does
everything anti-commutes with everything.
Okay, everything.
And the only anti-commutator that's not 0 is psi with psi dagger.
Yeah, okay.
And of course, we're going to soon have several psis and several didaggers, and so this will be delta ik or something.
So
Let's see, we've got some candy to give out. You asked the question, didn't you?
yeah, I have another one.
You asked a question. Another question.
Get through here for the third base. So, I guess, I mean, looking at this, it looks like that the next to last equation that you wrote there, then it's just saying that theta equals 0. Theta equals the vacuum.
Well, if you could factor out the theta, I mean, if you could divide by theta, you could say that.
Not really.
But it's not fair to divide by theta.
I wouldn't say dividing by theta, but theta is sort of an operator.
Well, I mean, what theta is, we got to think like mathematicians here. These are the rules. Theta squared is 0, and then integration goes in such a way, these are the integration rules. That's all, those are the rules that define everything. You can't then drag in something from the rest of, from complex mathematics into Grassmann mathematics. So we can take the inner product of zeta with theta. And so what I should have said back here is that once we have these two Grassmann variables, we have a lot of other Grassmann variables. And putting these two together, the computation is in the class notes, but I'll just tell you what the answer is. It's e to the zeta star theta minus a half zeta star zeta plus theta star theta. So it's very much like the coherent state formula, the inner product of two coherent states. What?
I just didn't notice these.
The difference is one uses the middle of the Greek alphabet instead of the beginning. Okay, a Gaussian integral. Let's integrate. So first of all, we've seen that the Grassmann integration is very simple. Gaussian integration, even with complex variables, is very simple. You put the two together, it gets super simple. So this is a Gaussian integral, e to the c theta star theta. And now we're going to do d theta star d theta. So the first thing is we expand the exponential and we get 1 plus c theta star theta. D theta star d theta. Then we know that the one term gives 0 because d theta is 0 and d theta star is 0. Those integrals are 0. So we just have a c integral theta star theta d theta star d theta. Okay, we move the theta across the d theta star. Well, let's see, I should have said to you that not only do Grassmann variables anti-commute with all fermionic operators, they also anti-commute with Grassmann differentials. And so this is minus c integral theta star d theta star theta d theta. But now the rules for theta d theta or d theta star, theta d theta is 1, theta star d theta star is 1. And so this is just minus c integral theta star d theta star, and that's 1 also. So the answer is minus c. So this Gaussian integral is just equal to minus c. So this, so if I write the thing again, since this is kind of important, e to the c, theta star theta, d theta star, d theta is minus c. Notice that if you were doing complex integration, it would be a 1 over c. And in fact, what you want, if you were doing complex integration, you want a minus sign here. I mean, if this were, you know, c star c, if this were z star z, then it would be positive. You'd want a minus sign here, and then you get a positive c over here, but instead of being c, it'd be 1 over c, or 1 over c squared. And you have to get the arithmetic right. I think it's 1 over c. So the next thing is to form the identity operator for a space of states. So the general space of states is C0 plus D1. And we can think of this as C on this vacuum state plus D psi dagger on the vacuum state. And it turns out that the identity operator is in fact, once again, very much like a coherent state relation. It's d theta star d theta. It's the outer product of the outer product of a Grassmann coherent state with itself integrated over all complex Grassmann space, which is anyway. Since you missed the beginning, it's all in the online notes. And so this, in fact, of course, is 0, 0 plus 1, 1. 1 being this and 0 that. And just for those who came in late, the most tricky, the weirdest thing, or most surprising thing in the whole business is you pick a reference or a fiducial state that's just not any state that's not annihilated by the fermionic annihilation operator. So you pick one and stay with it. Then you define, then you say that 0 is the fermionic annihilation operator with the fermionic field acting on this reference state, which isn't 0 because you've chosen it not to be. And then you have the fermionic annihilation operator immediately annihilates the vacuum state. So it's everything is all very logical, yes.
Should there be a star on one of these in the identity?
Well, no. In fact, when you do things if you were doing things in actual coherent states, this would be B2 alpha over pi, right?
Sure.
So it's just D real alpha, D imaginary alpha.
Okay.
And it's alpha and the adjoint. It's the ket alpha and the bra alpha. And this is the adjoint of that, but we write the adjoint this way. We don't, even though there's an alpha star in there, we don't write it that way.
Okay. So this outer product of theta with theta still has some contribution to the theta star integral? Because my only worry
Sure,
is that
sure,
the
sure.
integrator
Well,
of the star we get 0, right?
All right, look, here's theta, right?
Yeah.
So let me write down what theta star is. So here, minus C equals. Theta star is the adjoint of this. So it would be E to the theta star psi minus a half theta star theta.
Okay.
Sorry. Okay, so now what we're going to have is we're going to have a lot of theta i's and j's which anti-commute with each other. And of course also theta I star, theta j star anti-commute with each other. Theta I, theta j star anti-commute. So everything anti-commutes with everything. The only thing that isn't is an absolute it doesn't give 0 when you take the anti-commutator is delta ik for the fermionic operators. And the d theta is anti-commute, so psi I d theta 0, theta d theta 0, I, k, so forth, L, whatever. Okay, now the reference state is that you find a state such that psi ks is not equal to 0 for all k. So you want a state that's not annihilated by any of the fermionic annihilation operators. And then you then define your vacuum of the theory as the product k equals 1 to n of psi k on this state, this reference state S. And notice there are 2 degrees of arbitrariness in here. One is that this is an arbitrary state, but you just pick it and stay with it. The second is that you can, if you change the order in which you do the multiplication of the size, you change the sign of the vacuum state. But fortunately, it either goes from 1 to minus 1, and so it's not that arbitrary, it's just arbitrary to within a sign. And then you define a multi-particle coherent state, and this is e to the sum on k, let us say, psi k dagger, theta k, minus a half theta k star, theta k. All of that acting on our vacuum, which was defined up here. And one thing which is in the notes is that these eigenstates, of course, of the fermionic operators, this state theta little art, let me just write down the rule. The theta k on theta is just theta, I'm sorry, psi k on theta is theta k on theta. And so this theta is an eigenstate of all of the fermionic annihilation operators. And then we have an inner product rule that's just the multiple version of the one that I wrote down. And in fact, the easiest way to write it is just to imagine that zeta is a vector, and I'll just do zeta dagger, and then it's minus a half zeta dagger zeta plus theta dagger theta, where I'm taking theta as a vector and theta dagger as the row vector of complex or conjugate variables. And the identity operator now is an integral theta theta product d theta k star d theta k. And fortunately, the d thetas, the product of two d thetas is bosonic, and so, well, bosonic in the sense that it commutes with another one. So the identity operator is unique, and it better be unique because we know what an identity operator is. If you have well, we did the Gaussian integral over there. If you now do an arbitrary Gaussian integral, I'll just tell you what the answer is. E to the minus theta dagger A theta. A here is just a 2 by 2 matrix. D theta 1 star, D theta 1, D theta 2 star, D theta 2. And so what's a convention here is D theta I star, D theta I. Which order you have, whether you have 1s here and 2s there, or the reverse, doesn't matter. And what do we get? This turns out to be the determinant of A. You might say, where did the minus sign go? Well, previously I had a C here and a minus C there. And so now, in fact, I should have written that with the C in the other place, and it would have looked nicer. So this is the formula, and we can generalize this immediately from 2 by 2. And the reason why this works is you just write this out. And the only term that survives is a term that has 1 theta 1, 1 theta 1 star, 1 theta 2, and 1 theta 2 star. Well, that's the nature of a determinant. And so, in fact, that's why that works. And the generalization to n by n matrices is e to the minus theta dagger A theta plus theta dagger zeta plus zeta dagger theta product d theta star d theta. This is determinant of A times e to the zeta star A inverse zeta. That's actually an important formula. And let me tell you, let me remind you what the formula is for a complex, in ordinary mathematics, as a complex integration. In other words, the Gaussian integral formula is e to the minus y dagger s y. S is just an n by n matrix. Plus, and for some reason I had a 2. 2i c I have this as C transpose Y, which I think is sort of unfortunate. Anyway, dy1 dot 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 dyn. So these are real variables as opposed to complex variables. And the answer then is pi to the n over determinant of s to the 1/2 e to the minus c transpose s inverse c. So you see, it's a very similar formula. The difference is the determinant is in the numerator in the Grassmann case, the denominator in the denominator in the complex case, numerator in the Grassmann case. And in fact, if you think about 0-point energies for the moment, and here I was sort of going back to the path integral business and computing the energy. If you wanted the energy, what you do is you do a derivative, and in this case, you're differentiating with respect to this guy in the denominator, and here you're differentiating in the numerator. There's a difference in sign, and that's why the energies of fermions are negative, whereas the energies of bosons, the 0-point energies of fermions are negative, 0-point energies of bosons are positive. And that, of course, is one of the things that people like about supersymmetry. That's something I like about supersymmetry, but whether nature cares is not known. So just as with quantum field theory, you can define, in fact, we can imagine that this index k labels the points on a spatial lattice, and then we can allow time to go forward, or we could even say that the size, that k labels the points on a 4-dimensional space-time lattice, and then we can let the lattice spacing go to 0, and then we go to a Grassmann field theory. Now what we've got then is chi I'm calling the Grassmann variables now. So theta Grassmann is going to go to chi so that it looks more like a Fermi field. Oh, let me just mention something. You see this statement here that the vacuum is the product of all the annihilation operators on a state that is not annihilated by any annihilation operator. This reminds me of the Dirac sea. So I'll just write this down. Of course, I have to spell C, S-E-A, no E-S-A. But it reminds me of the Dirac sea. Maybe it doesn't remind you, and maybe it had nothing to do with Dirac sea, but there's something there that's similar. So now we're going to talk about a field of Grassmann variables. And so we'd have, and we can have a star or no star. Doesn't matter, since it's Grassmann, it's going to be 0. And then we're going to have, of course, our actual fermionic fields, psi m of x and t, psi n dagger of, let us say, y and t, an equal time anti-commutator. We want this to be delta mn delta cubed of x minus y. So those are the anti-commutation relations for the fermionic fields. And here I'm imagining m and n to go 1, 2, 3, 4. In other words, these are just the 4 components of a Dirac field. Of course, one could say, no, these NMs are the 4 components of the Dirac field, and then another label that says which Dirac field. Electron, muon, red up quark, blue down quark, whatever. And so the formula for a coherent state now this is a functional coherent state. This is E, and now it's an integral. Psi dagger of, let us say, x, chi of x, and this inner product is over the index n, minus a half chi dagger chi, again, of x, d cubed x, 0. And this is an eigenstate of all the annihilation operators. Of course, one does this, since this depends on time, this is at a particular time. Let's say the time is 0, and this is chi m of x chi. So this is an eigenstate of all the fermionic operators, but the eigenvalue of this eigenstate is a Grassmann eigenvalue of this Grassmann coherent state. And the inner product is the thing you expect. E to the integral chi prime dagger chi minus a half chi prime dagger chi prime minus a half chi dagger chi d cubed x. And 1 is equal to an integral of chi pi d chi star d chi, where this means you integrate over all of the variables. Now, yes?
So over here we had subscripts in the chi-m's and the size, and then
Say that again?
over here we had subscripts on the chi-m's and size, and then up in this integral, we don't have subscripts anymore?
Well,
Are we like some?
chi dagger chi.
Oh, okay.
Let me get you a candy. I'm getting low again here. Candy face. So the Hamiltonian for a single Fermi field not interacting with anything else in Weinberg's notation is gamma dot grad plus m psi d cubed x. And whatever you say about Weinberg's notation, when it turns out, when it comes to the Hamiltonian, it's a very nice expression. The alternative notation has an I there. But, of course, the I gets absorbed in a psi bar. And, of course, the gammas have the usual relation. Gamma A, gamma B is 2 A to AB. Well, that's it, 2 A to AB. And well, now let me just, well, I'll write down one, I'll skip a couple of steps and writing down one formula. Chi prime, keep in mind, if we want to do a path integral, then let's, let me first of all mention something about the standard model and most ordinary quantum field theories. Most ordinary quantum field theories are quadratic in Fermi fields. You almost never have a linear term in Fermi fields. You almost never have a cubic term in Fermi fields. And you almost never have a quartic term in Fermi fields. That's true at least of the standard model and all normalizable field theories. One exception to this was Fermi's theory in 1934, I think, of the weak interactions, because that theory was an effective theory field theory, and the true theory is the Weinberg, Glashow-Weinberg-Salam, Glashow-Salam-Weinberg theory. Okay. So let's construct the path integral then. This thing is quadratic. I'm writing it in as simply H0, but if it had any other terms, it wouldn't really matter because they'd have to be quadratic. And so what we get here is, it turns out to be e to the epsilon integral a half chi dot dagger chi. I'm skipping steps that are in the notes. And I hope I'm copying the notes correctly. Okay. Now, what's nice about this, and here again I'm going to be skipping a lot of steps because we only have one more lecture in this course, right? Which is next Thursday. That's still the exam day. Okay. So let me just say what one actually gets. So what I'm going to write then here is chi prime e to the chi prime sub t e to the minus 2i t h0 chi at minus t, and this label is this is just a coherent state, another coherent state. But I'm labeling them as t and minus t to explain why I have a factor of 2 there. And following these steps, what we get is that this is e to the I integral L0 of chi d4x d chi star d chi. In other words, we get, for any quadratic Hamiltonian, we wind up with exactly the same, formally the same expression as we had with simple as we had with ordinary bosonic field theories. In other words, the matrix element of the time evolution operator is a path integral of exponentials of in which the phase is the phase of the classical action, and you integrate over all paths. And so one could equally well write this as e to the I S0 of chi d chi star d chi. So that's that, and well, let me skip to the end because we do need to move a little bit quickly here. So the time-ordered product then of actual fermionic operators, psi bar x1 dot 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 psi x 2n, and I've put an even number of Fermi fields because if you take the mean value in the vacuum of an odd number of Fermi fields, you will always get 0. And this is then a ratio, and it's a ratio now of a Grassmann field, chi of x1 dot 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 chi of x2n e to the I S0 of all the chi's putting in an epsilon, which is the I epsilon thing. D chi star, D chi, and dividing that, of course, by e to the I S0 chi epsilon d chi star d chi. And one can also define a nice thing, Z0 of zeta as 0 t e to the integral zeta bar psi plus psi bar zeta d4th x. So this is a thing that you can define, and this turns out to be, well, you just use this formula, and so this gives you an integral of e to the integral zeta bar chi plus chi bar zeta e to the I S0 chi and epsilon d chi star d chi divided by the same thing without the exponential. Okay, well, one can derive from this Feynman's propagator and so forth. I think I'll stop the fermionic path integrals here, and I'll also stop the path integral chapter here, and now switch over to something else. In fact, I think the something else that I'm going to do, I was going to...
I'm sorry.
No, it's not your fault. By the way, did anybody ask a question and not get a candy? Okay. I was going to... I prepared notes for starting on the renormalization group, but I thought instead I would say a little more about the Higgs mechanism. Maybe what I'll do is I'll just extemporaneously say a few more things about the Higgs mechanism, because I want to give you a homework problem on it, and I think I need to say more about it before giving you a homework problem. So let me do that. And the homework problem is due the day of the exam, which is next Thursday. But it's going to be, I'm not going to...
No, there's just a
I unfortunately haven't brought my notes on the on this, so they exist, but it's just I didn't think I was going to do this, but now I think I should. So let's look at at something very simple. Let's suppose we just have a theory that is minus what shall we call it? Phi dagger phi, well, d mu, dA, say, dA phi, oh God, the writing is terrible, plus m squared phi star phi. This is just a complex field. And maybe I'll just leave it like that, and rather than put in any factors of 2. So this is a theory in which the minimum, if we look in the complex space, so I'm drawing the complex plane like that, in such a way to say that if the energy density V, of course, is lambda, well, it's absolute value of phi to the 4th minus m squared absolute value of phi squared. And so at phi equals 0, it's 0, but then it goes down like this, and the minimum is basically here, but then it starts to go up, so that, and it goes up like that, from that, and so what you've got is, you've got a minimum that's a circle around the origin, and the minimum value of the circle is when v is 0, and if you differentiate with respect to phi squared, you get 2 lambda phi squared minus m squared, so absolute value of phi squared is m squared over 2 lambda. And so this is the absolute value squared of phi in the minimum. And now you'd say, well, what are the masses of this theory? This theory has 2 real fields. In other words, phi is 1 over root 2, phi 1 plus I phi 2. I think I'm going to be doing the homework problem for you right now, so which sort of makes it stupid that I'm even assigning it. But in any event, if you look at, well, for a normal field theory, let me just tell you for a normal field theory. For normal field theory, the Lagrangian is a single field theory. It's minus a half dA phi minus m squared over 2 phi squared. That's a single real free field. And the mass of the field is m. And in fact, if you write down the equation of motion, you can see that that is the mass of the field. In other words, the equation of motion is box, that's supposed to be a box, plus or minus m squared phi equals 0. And I think actually it is a plus sign, but anyway, it's a plus or a minus sign. Now what you do is you say, well, let's suppose the field, let's pick, and frankly this is something that people always say, and as far as I know, I've never seen a really good treatment of this, to tell you the truth. In fact, I remember Gaussian at a UNM colloquium years ago in which he used the phrase, now I'm trying to reproduce a Gaussian phrase, and I'll probably screw it up. Anyway, he said the vacuum picks an asymmetrical minimum from a symmetrical state, from a symmetrical set of asymmetrical minima. So we can say that our phi 0 field will be simply 1 over root 2, and what does it have to be? Well, 1 over root 2 squared has to be that, and so this is m over, in fact it's m over square root of lambda, and I don't know if I've got the root 2 right or not, but if we choose the point here, well, I haven't drawn this very well. Anyway, on the circle, any point on this circle of radius squared, m squared over 2 lambda, any of those points is okay. And if we pick, in fact, this point here, where where phi 2 is 0 and phi 1 is this, then we can say that phi is equal to 1 over root 2, and I'll just call this thing v. V plus delta phi 1 perhaps, plus I delta phi 2. So you can think of these as the quantum vibrations about V, which is the classical vacuum. And now if you take this expression and put it back in here, and you ask yourself, what does it look like? Well, what it'll look like is that L0 now will have a term in which you'll have something like delta phi 1 squared v squared times some number that's like a half or 1 or something, maybe 2. and then it will be plus delta phi 2 squared. And no, there isn't any, there won't be any delta phi 2 squared. There won't be any term like that. And so this will be the quadratic part of this. Okay? And so what will you say? Well, you'll say then that the mass of phi 1 is apart from a factor of root 2 or something, it's V. In fact, that'll be the homework problem to fix up all my screw-ups. But on the other hand, M2 is 0 because there isn't anything there isn't a quadratic term in V2. There will be cubic and quartic terms. In fact, if you want, you can put in plus lambda phi to the 4th, and you can stick that. Well, that no. Hold on. This was an example of the most elementary field at an exact mass. What I meant for you to do was to take this field and put it in here, and then look for the quadratic parts and identify the masses. Okay, well, I'm terrible with names, but one of these is called a Goldstone boson, and I think it's the one that has mass 0. And so what happens now instead if we do the same thing but with a an electromagnetic field as well as this complex field phi, and so anyway, what I'm trying to do here is just sort of give you enough so that you can do the homework problem. So now our Lagrangian is going to be minus du phi star, well, I've switched to Greek, sorry, du phi minus m squared phi squared plus, actually it's minus here and plus there. And then minus a quarter f mu nu, and I think that's the whole story. And as I say, you're going to have to get these numbers right. D mu phi is the ordinary derivative, and then plus or minus i.e. a mu phi. So as I said, I don't have my notes, so I'm minus signs, plus signs. I once was at a lecture, and the string theorist who said he was going to set h bar c minus 1 I and minus and I and pi and 2 equal to 1. And then he went on with the lecture. So in other words, all of these trivial factors he was ignoring, which is fine. Okay, so what happens here, you see, is that once again, phi is going to have some value. It's going to be some v, which is the asymmetrical minimum selected from a symmetrical set of asymmetrical minima of the phi vacuum. And then, and we'll say that it is then plus delta phi 1 plus I delta phi 2. And in fact, this might have a 1 over root 2 here. And so then if you look in here, you're going to see that there's going to be a term like this with a minus sign. And that means that the gauge field, A mu, gets a mass, and the mass of the mass squared of the gauge field is proportional. In fact, it's not V, it's E squared V squared. because there's an E here. And so the mass squared of the gauge field will be that. The mass of the phi field, phi1, will be V. And now what happens to phi2? Well, the phi2 mass, the phi2 degree of freedom goes into the gauge field. So the thing that's, you see, the thing that's actually now the mass term, let's see if I can get this right. You see, F mu nu is d mu a nu minus v nu a mu, of course. And if we define a new field, b mu, say we say b mu is a mu plus d mu phi. And I'm going to need a constant here and maybe a minus sign, but it doesn't matter. But because this is also going to be d mu b nu minus d nu b mu. So if you shift A to B, you have the same, you haven't changed the F term. And now in this thing, absolute value squared, what you're going to have is, you see, you're going to have d mu phi plus, well, let's just do a plus sign, I a mu phi. We've got this squared, basically, or absolute value squared. And, but we're saying that a mu is b mu minus d mu phi. And so this is essentially, E b mu well, not quite, is it? Well, maybe I should write out what it actually is, because this is what's happening. So let's suppose we did this change. Then this would be d mu phi plus IE, and now it's b mu minus d mu phi times phi squared. I thought this was going to work out, but it now looks a little bit funny. In fact, it looks very funny. Maybe one should. Actually, you know what? No, I'm just getting an idea here. Suppose we wrote this as d mu log phi. Now so that's a 1 over phi. So this would be a 1 over phi, wouldn't it? This would be d mu phi over phi. Right. So this looks now starting to look a little better, because now the phi's cancel in this term, and this d mu cancels that one. Again, if I have the i's and the e's. Remember I said IE. This turns out to be just b mu e squared b mu phi, no, just e b mu phi squared. But phi, the mean value of phi is v, and so this is just e squared v squared b mu squared. So in other words, this whole term, apart from the, or part of this whole term, let me put it that way, part of this whole term is simply the mass term for b mu. So that's another way of thinking about it. In other words, there's a new field, and you can think of it as b mu as a mu plus the derivative of log of the scalar field. Anyway, so what I'd like you to do as the homework problem for next Thursday is to kind of work this out with all the factors of plus or minus 1 and minus signs. I'll define the thing, correctly for you, and then you can go through it. And since I did this on the spur of the moment, I don't absolutely guarantee it, although in a certain kind of theory it does work. So maybe I will go back to my notes now, and I'm going to say something about the lambda phi to the fourth theory, but I haven't erased the boards. So let me just. I'll have to do it. I'll have to erase this. One do? Does one eventually clean this rag? Or does it just keep absorbing this stuff until erasing has no effect? I don't know. So let me start just saying what happens if we have this a simpler version of the theory? It's minus a half di phi, so this is a single real scalar field with a normal mass minus a half m squared phi squared minus g at this time over 4 factorial phi to the fourth. And what happens if we work this out? Well, the lowest order Feynman diagram for the scattering of two bosons is, of course, just like that. Just this term here to the lowest order. Then in second order, we have a bunch of diagrams, and one of them looks like this. 1, 2 goes to 1 prime, 2 prime. This is called the S channel. And then the other two look like this. 1, 1 prime, 2, 2 prime. This is called the T channel. And then the other one is 1, 2, 2 prime, 1 prime. This is called the U channel. And by the way, I'm taking this from Weinberg's chapter 11, section 2, and chapter 12, section 2. So what does one get? Well, the amplitude for this one, plus this one, plus this one, plus this one is, and this is, I'm taking this directly from Weinberg, so he's writing the thing down in such a way as to just follow his formulation of the Feynman rules directly. And down here it's 2 pi to the 6th, 16, and then E1 dot 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 E2 prime. So it's product of twice all the energies, so 2 to the 4th is 16. And what is F? Well, F is minus I, 2 pi to the 4th times F is First, the lowest order term is minus I 2 pi to the 4th g plus a half. So this presumably is what you guys calculated and turned in today. Plus a half, and this is minus I 2 pi to the 4th g squared minus I over 2 pi to the 4th squared, and then it's times an integral d4 k. And it's actually 3 integrals. The first one is 1 over, well, what do we have here? We have a propagator, so that will give us a q1 plus k squared, and so this is q1 right here, and let us say that this is q1 plus k, and if that's q1 plus k, then this would be q2 minus k, and this, the Feynman propagator, is plus m squared minus I epsilon. And now, because we're in the one loop order, we have to keep the I epsilons. And the next factor is 1 over, well, it's the other propagator, and that's q2 minus k squared plus m squared minus I epsilon. And then the other terms are just what you would do to change the denominators. So this over here, you've got again q1, but now, and here you have q2, and you have to choose what you call these. So you'll have, one of these might be, this thing might be q2 minus k or plus k. Anyway, you've got, let me just call these, just let q2 go to minus q1 prime, and then the other term is q2 goes to minus q2 prime. So you change these variables, and you get these different actual values. And I think what Weinberg means when he uses this shorthand is that you take this product here, and you take into account the energy momentum conserving delta function when you make this change. I see I'm over time. All right, let me just stop. I'll say what I'm going to do next is show you a Feynman trick, a Wick rotation. Maybe I'll mention something about dimensional regularization on Thursday, and then say something about the renormalization group in various contexts, quantum field theory and condensed matter physics. All right, we can stop now, I think.